Okay. Okay, so does everyone know what if I ask you to draw the device level view of a MOSFET, do you know what it looks like? Have you studied that in the analog electronics course? So for example, one of the ways we represent MOSFETs, the device level, is like this. So you have an N plus, so this is an NMOS, for example. Right, you must have seen pictures like this, right? So typically if you take a real, even if you take an discrete MOSFET, it will look something like this. Most of the ICs, you try to create multiple MOSFETs on the same substrate, right? So the idea is, you take the same substrate. So obviously these N plus regions are the drain and source connections. You have the oxide, and then you have the gate. Okay. Obviously the MOSFET is a 4-terminal device, so you also have the bulk. Okay. Remember that the MOSFET is a 4-terminal device. Okay. Even though you use 3 of the terminals for most of your analysis, it really is a 4-terminal device, and the 4th terminal is extremely important. Is that clear? Okay. Now on the same, let's say on the same substrate, you want to create a PMOS. Okay. So obviously the PMOS bulk is an N-type bulk, and it has P plus diffusions for the drain and source. Right. So you have an N well. You have 2 P plus diffusions, right, for the PMOS. And now let me just modify this slightly. Yeah, sure. People who want to move to this side, I think, yeah, you might want to move to this side. Okay. I think if it's a major problem, I might reconsider and just start using the board. But let's try to do it from this side and see if we can. Okay. You guys are able to see pretty well. It's not so clear, is it? Am I blocking part of it? Okay. Then, okay. Obviously, we have to. Can you go to the? You want to try it from that side, from the back? There is still some space, or maybe there. Obviously, if you go to the back, it'll get better. Hopefully, you can still see. Sandeep, are you able to see what I'm writing? Is it big enough? Okay. By the way, before that, just remembered. So we have 5 TAs for this course. So can the TAs please stand up? I think 3 of them are here. So that's Sandeep, that's Radha, and that's Venkatesh. Okay, from my left to right. Okay. So there are 3 of the TAs. The other 2 TAs will be attending the class, I hope, next time. So they'll be conducting the tutorials and helping you with homeworks and so on. Okay. If you have any questions, you're welcome to ask them. If you want, you can set up an appointment with me if you have any questions. Okay, that's also fine. Probably from next week, or the week after that, I'll start having regular weekly hours. Okay, so when you can come and meet me. Okay, so back to the topic, right? So now you have the NMOS and the PMOS. What other kinds of circuits do you need? You need, let's say, you need to make connections, right? So you need metal lines to connect, let's say, the drain, gate, source, bulk connections. So you also have on the same substrate. So let's say this is the poly. Okay. You also have multiple metal layers. So typically these CMOS ICs have multiple layers. Okay. For example, you can think of the P substrate as you start off with the P substrate, and then you, for example, grow your N plus diffusions. On top of that, you deposit oxide, right? And again, on top of that, you deposit the polysilicon, which is the gate. Okay. And similarly, this is your oxide here. Above the polysilicon, there is another layer of oxide. Then you have metal. Now, let's say you want to make the gate connection. So let's say this is a gate. You want to make a gate connection. Then you do what is called a via. Okay. A via is basically takes you from one layer to the next layer. Okay. Similarly, you would have a different kind of via if you want to connect these. So these will be called M1. Modern IC processors have something like 5 or 6 layers typically. Okay, because you have a lot of complex circuits, you want to make a lot of connections, so they'll typically have a lot of layers. Okay. Now, later in today's class, we'll also discuss how to make other components. For example, you're interested in resistors, capacitors, right? I think pretty much analog circuits, resistors, capacitors are, you'll stop with that. Later, some of you might take an RF circuit design course where you'll learn how to make inductors, right? Those are also quite important. Okay? Okay. What do you do with the, now, did you talk about, in the previous class, did you talk about what to do with the fourth terminal of the MOSFET? Or you consider the MOSFET as a 3-terminal device? 3-terminal pretty much, right? So what you have to do is, if you have an NMOS, so typically the P substrate, you have to connect it to the most negative voltage available in your circuit. Okay? That will make sure that your junctions, PN junctions, are reverse biased. So you don't have forward biased junctions in your circuit. Okay? So that's for the P substrate, and that's common. Remember that that's a common connection for all your NMOS transistors. However, if you have an NMOS really far away, right, you may have a central connection to the negative terminal. If you have an NMOS very far away, obviously the connection for that is going to go through some very resistive connection. Right, the actual bulk for that is very resistive. So you probably want to put in, local contacts. So you might put in P plus contacts and connect it through metal. So let's say this is usually ground. Okay. In most of these modern IC, you would have studied like in op-amps, you would have studied -15 plus 15 volt supplies. Okay. In most of these modern IC circuits, you don't have negative supplies. You have a ground and you have a positive supply. Okay, so you'll connect your P substrate to ground, and the better way to do that is to put in P plus contacts and connect it to ground using metal. Okay, you're connecting using metal to ground so that you have a very good connection instead of this very resistive connection. Okay. And the other thing, if you look at the same transistor in the top view, okay, so this is your gate, this is your drain, this is your source. So you're just looking at the top view of this is the side view. Of the NMOS. You have the drain, you have the source, you have the gate. Okay, where do you have the bulk? So in reality, so let's say you had a, let's put in a P plus. So let's say you have a P plus connection to ground, even for this MOSFET. Okay, so you would have bulk contacts here. Give me a second. Okay. This is the length of the MOSFET. Right? You would have studied that last time. This is the length of the MOSFET. Correct? That's the channel going from the drain to the source. This is the width of the MOSFET. Okay? And usually, this is the third dimension. Let's say the depth of the diffusion for the drain source. That's usually a constant. Okay? And same thing, this dimension here. Okay, you can the depth dimension is constant. The lateral dimension here, let's call it x. That is usually kept to a minimum for reasons we'll look at later in the course. But you can change that too. Okay. Okay. How about resistors? So we looked at the MOSFET. Okay. Next type of device is the resistor. So you actually have several kinds of resistors. You have polysilicon, which is usually the material which makes up the gate of the transistor. And then you have several kinds of diffusion transistors. Diffusion means, for example, you have the N-well. You can use a piece of silicon. If you take a piece of silicon, it has some resistance. You can use that as the resistor, right? You have the N-well resistors, N plus and P plus diffusions, which is the drain source diffusion. You have metal connections, right? M1 to M6. You can use the resistance of the metal lines. Okay. And I don't know if you studied this. A MOSFET in the triode region can be made to behave like a resistor. Okay. So these are the different kinds of resistors you have available to you. Now each one of these has certain advantages, certain disadvantages for certain applications. Okay. So what are you most interested in? Okay. So one of the things you're interested in the resistance value for a given area. Okay. So in other words, so one of the things you'll see differences between discrete circuit design and IC design. In ICs, every micron of space on the circuit is extremely important. On the integrated circuit is extremely important. Okay, so area comes at a premium. It costs. So you have every micron or every millimeter of area costs money. So you want to minimize it. So if you want, let's say 20 kilo ohms, you probably want to make it very compact. Okay, so that would be one parameter you're interested in. The other thing you're interested in is linearity. Obviously the resistance, if you take a MOSFET in the triode region, for example, it's linear for very small voltages, but as you keep increasing the voltage, it becomes non-linear, right? We know that. Similarly, many of these resistors, you'll find that they're linear for maybe for small voltages, but they can become non-linear for larger voltages. Okay? The other thing you'll be interested in is the temperature coefficient. Okay? So ideally you want the resistance value to be constant with temperature. But I'm sure you have all done a course in solid state devices, right? You know that for a semiconductor, a lot of things depend on temperature, right? Including mobility, for example, right? So that would pretty much mean that if you take a piece of silicon, you're trying to make a resistor with it, there will be a fairly large temperature coefficient compared to normal materials, right? So that is the third thing you are interested in. Okay. So if you look at polysilicon, so okay, except for the metal, right? Most of the others are going to have some amount of temperature change because they all depend on semiconductors. Okay. The metal obviously will have a little bit less because it depends on the expansion contraction that you know from your basic physics, right? But obviously this is very low resistivity, right? So it will be a few milliohms per for a given length. Okay. Yes. Okay. I thought somebody had a question. Okay. So it will be a few milliohms for the resistance. Okay. One of the things you can define for many of these resistors is what is called sheet resistance. Okay. So if you take a piece of, let's say take a piece of semiconductor and has a certain length It has a certain width, and if you look at the this is the top view. So it has a certain thickness T. Okay. Any resistor you make will have these physical dimensions. Okay. Now for most of these things, you can vary L, you can vary W to change the resistance. But the thickness is usually set by the process. You don't have any control over that. Okay. So what that means is, right, your resistance is nothing but rho L by A, right? A is nothing but T times W. That's your cross-sectional area. So let's assume that current is flowing like this. That's an assumption I'm making along the length, right? And this guy actually for a particular material and for a particular thickness is constant. So this is represented by something called the sheet resistance. Okay. And it's usually represented in ohms per square. Because what that means is, you can take your, let me erase this for a moment. You can take this, okay, let's assume it's very long, but in this case, maybe this is, if you take L by W, it's, in this case, let's say it's 2.5 squares, right? So I have, let's say 2.5 squares, okay? Which means if you have a particular sheet resistance, you automatically know the resistance of a particular length of device, okay? And for each one of these, you can define a sheet resistance for the N plus diffusion, for the N well, for all of these, okay? And normally if you look at the sheet resistance for all of these, this will be of the order of milliohms per square. If you look at the polysilicon, it will be somewhere, ohms, several ohms to several tens of ohms, maybe all the way up to 100 ohms. Okay. If you look at these guys, you can have several hundreds of ohms. Again, tens of ohms to several hundreds of ohms. And the N well would have kilo ohms per square. So in other words, if you take a single square piece of N well, it will have several kilo ohms of sheet resistance. It doesn't matter, right? So as long as your L by W has a certain ratio, let's say if you have 1 square, L by W is 1, right? So in other words, you'll have RSH would be your resistance, right? If your length is twice your width, you'll have 2 RSH. Okay? Is that clear to everyone? Okay. So now, depending on, the value of resistance you want, and obviously the other things we discussed, right? Density. Let's say you're interested only in density, you don't care about linearity, you don't care about tempo, you would obviously go with the N well resistor. Okay? But let's say you want a perfectly linear resistance, you probably go with the poly or the metal. Okay, metal typically, unless you want only a few ohms, right? You probably don't want to go beyond, use the metal for any of these resistors anyways. Okay? So let's say we take and obviously the sheet resistance is defined actually by a lot of device parameters. Okay, so one of the reasons why you have, let's go back to your device. One of the reasons why for example, your N well has a very large resistivity, right? Very large sheet resistance is because it's a very lightly doped substrate. Okay, so it's N wells are typically very lightly doped, so they have very large resistivities. If you look at your diffusions, right, they usually have very low, so you'll get in tens of ohms, okay, all the way up to maybe 100 ohms or something, okay, and those will be again more heavily doped. Polysilicon would again have very low resistivities. Obviously metal, I don't even have to tell you, it's typically, it just depends on the material, right? In most of these processes, it's either aluminum or copper. Okay. So if you have, let's say, take the case of N-well resistors, right? Okay, an N-well resistor could look something like this. So you have a, obviously the length is given by this parameter, but you have a certain, so you have these, let me call this P1 and P2. Okay, those are the two nodes of the resistor. Okay, why do you need these N plus diffusions? To make a good contact to the actual resistance. The actual resistance comes here between these two nodes, but to make a good contact, you need to give N plus diffusions. Okay, the connection to the rest of the circuit will happen on metal. So this will be, so let's call this P1, P2. So you'll get some resistance here. And we just discussed that it's a few kilo ohms, right? Now, let's see what happens. So let's say, okay. So now, let's say one node is at 1 volt, other node is at 1.5 volts. I mean, this is an easy, you could have something like this. So let's say this is 1.5, and let's say this is at 1 volt. Okay, that's the output. Let's say you take a resistive amplifier. Okay, so you could easily have a case. So what happens? So now this N-well to P substrate, you have it's a reverse bias diode. So you have a certain depletion region, right? So you'd have a certain depletion region here. Okay, you'll have a certain width based on this voltage. Remember that this thing is going to be connected to, let's say, ground. Okay. Now let's say this goes from 1 volt to, let's say, 1.2 volts. What is going to happen to the depletion region? It's going to increase, right? The width of the depletion region is going to increase because the actual reverse bias on the N plus P diode is changing. So it could become something like this. Okay. What does this mean? It means that, so obviously you are depending on the movement of charge carriers through the N-well to get your resistance. If this voltage changes, the depletion region changes, that means that the resistance of your N-well between those two nodes is going to change, right? So in reality, it could very much look like this. Your current to voltage, this is your ideal situation. Could be some kind of nonlinear relationship. Okay. So in cases where linearity is very important, and if you use it in cases like this, it probably is quite important. Okay. You don't want to use an N-well resistor in most cases. How about a poly resistor? Actually, let me go to the next page. Let's take a poly resistor. Okay. What do you have? So this is your ground. Okay. You're also going to have capacitance. So this poly, so what happens? What is the, if you look at all the intermediate regions, right? They're all covered with oxide. Okay. Between all these layers, you have oxide. Okay. In other words, you have a dielectric material between two conductor substrates. So it's effectively a capacitance. It's like a parallel plate capacitor, and it's a distributed capacitance. So if you have a certain length, so you probably want to model it, let's say you model it in 4 sections. You may end up modeling it like this: P1, P2. Let me call this bulk. Okay, so let's say R by 4, So you could model it. So the main idea to understand is every resistor has, some parasitic capacitance that goes with it. Okay, so this is another thing you would choose. So if you are interested in a very wideband application, if you have a very high frequency signal, for example, you want to be careful about the capacitance. Okay, and obviously this capacitance will vary when you change the type of resistor. Okay. How about capacitors? So normally you have two kinds. So you have this is the standard, passive parallel plate capacitor. Okay, so you have a metal, you have two metals, and you have an insulator in between them. This insulator could be the standard oxide. It could be some special material. What are called high K materials. So they have very high dielectric coefficients. It will be more linear than the N-well. Okay, it will definitely be more linear than the N-well, because the polysilicon you're actually interested in a very low resistivity, and it's not directly connected to the substrate. Okay, so you will have better linearity for sure than your N-well. Okay, sorry, it depends. Okay, so it depends on the value of the resistance you want. Okay, if you want only a few tens of ohms, yeah, your capacitance may not, maybe low enough. Remember that because the resistivity is low, if you want, let's say, hundreds of ohms, if you make a very long poly, okay, you'll have a lot of capacitance because you have a lot of area under your poly. Is that clear? So obviously it depends on the particular application, the type of resistor you'll choose, and what is more important. So the other kind of capacitance widely used is the MOSFET capacitance. Okay, I'm sure you have studied the characteristics of the MOSFET. What happens to the capacitance? Have you studied that? I'm sure in the analog electronics course, right? So it actually, so if I plot C versus V, so let's take the case of this is your fourth terminal, okay? I'm going to connect the drain and source to your bulk, and I'm going to connect it. I'm going to plot capacitance versus VGB. Okay, you'll get something like this. Have you studied? You must have studied this before, right? I'm sure in your devices course you must have studied this, right? Start off with accumulation at very low voltages, right? Then you have depletion, then you have mild, medium, and moderate and strong inversion regions, right? So ideally, if you want very high density and linear caps, you want to operate here in these two regions, right? You want to operate in those two regions, and you want to make sure that, let's say you have a very large signal between your gate and bulb. You want to make sure that the signal does not cross over into the depletion or your or maybe your mild inversion regions. Okay, is that clear? So let's say you take two pieces of, let's say this is M1, M2, and you have oxide here. Okay, and let's say the distance between these is again T. This is often called a MOM cap, so it's a metal oxide metal cap. Okay. Okay, so this is of course your side view. Look at the top view, you'll only see you'll only see M2. M1 is right below it. Okay, so you create a certain width and length. Your capacitance will be epsilon times WL over T. Correct? So again, you can define a constant because the distance between the two metal layers is not variable. Okay? So these two things are a constant for a given process. Okay? So this is represented as cap per unit area. Okay? So usually you'll see things like femtofarad per micron squared, for example, right? Or maybe picofarad per micron squared, attofarad per micron squared. Those are the kind of dimensions you'll see for these capacitances. Okay? So now, what you'll find is in many of these processes, these caps are going to be actually quite, the MOS caps are going to be fairly dense. Okay? But these MOM caps, especially if you just use the oxide instead of high K dielectric, they are not very dense. Okay? Typically you'll find that the MOS caps have like at least 2 to 3 times the density of the MOM caps. Okay? So, if you want to increase the density, there are 2 ways to increase the density. So, which are, you know, you can use both of them. So, one is to use the comb structure. Yes. Because you are interested in area. If you want 1 picofarad capacitance, because area costs money, you want to get as much capacitance as possible in a given area, in a smaller area. Okay? That's the fundamental reason. Again, it all boils down to cost. Okay? Obviously, it's performance first and then cost. Okay? There's no use getting a very highly dense circuit which doesn't work. Right? Okay? So one way, okay, if you see, here, we're actually using the capacitance between M2 and M1. But, you can also do this. Okay? You can also do this. You take 2 capacitors, you take 2 metal lines on the same layer, place them very close to each other, you're going to have a parallel plate capacitance between them. Now the problem with this is that, now this dimension you can control, you can place them very close to each other. Okay, probably closer than the 2 metal layers. However, the area is the problem, right? Because now, this dimension is fixed, the thickness of the metal layer is fixed. Right? So you might need a very large metal line, right, or a piece of metal to actually create this capacitance. Okay, but you can actually do, do things to improve. So you can do both of these, right? You can do one of these, and then you can also get metal layer to metal layer capacitance also. You can do both of these. So one way to increase this, obviously you're interested in sidewall area between 2 metals, right? For a given area, you're interested in the sidewall area between these 2 metal lines. You can do something like this. So this is node 1 and this is node 2 for the capacitor. You get a lot of area. For a, you only have this given area, but if you just use 2 pieces of metal, you would have got very little capacitance. You can try to increase the lateral area between those 2. Okay. Similarly, the other thing you can do is, so this is on, let's say M2, this is also on M2, on the same metal layer. Okay, so you're basically doing something like this, on the same metal layer. This is the top view now. Okay, this is the side view, this is the top view. Okay, and you can also do the same thing. Now if you look at the side view for this, you can also do the same thing like this. So let's say this is M1, M2. Let's say you have 4 metal layers. You can do this comb structure on each one of those layers. Okay, so for example, you'd have something like this. Okay, you could have a comb structure. This is a side view, and you could also combine these guys. For example, you could combine these two guys. These two guys. You'd have some capacitance here. Right? That will increase the density even further because you only have a given vertical area. Right? So if you look at this, these are the dimensions you are interested in. Okay? L and W. Okay? If you use multiple layers below that, you are perfectly welcome to do that. That doesn't increase the cost. Okay? Okay, so I think, let me see, should we stop here? Okay, so maybe we'll just do one more thing. So we'll continue next class, but so you have the concept of a process node. So in other words, when you studied, for example, in the analog circuits course, you assumed that W by L was I don't know if you changed L a lot. You probably did because for output impedance and so on. But you assumed what you're more worried about was the W over L quantity because that pretty much defined a lot of things in your circuit, right? So one of the things you'll see is you have what is called scaling of your IC. In other words, you're trying to make the dimensions smaller, okay, smaller and smaller, starting off with the length of the MOSFET. Okay, so you're starting off with, so you have a whole range, so it starts off from maybe 5 microns all the way down to the latest process node could be 28 nanometers or 20 nanometers. Okay, so you have a whole host of processes available to you. You choose a particular process depending on cost, performance and so on. Okay, and obviously if you keep reducing the length for a given W over L, width will also reduce, right? So you actually get a smaller device. In other words, you can actually pack in more number of devices for a given area, right? So it becomes more area efficient. That is the idea. So you have, for example, so you have on either side, these are typical numbers you'll see. I think most probably in this course we'll work with a 0.13 micron process for your projects. But these are the kind typically, nowadays, there are people working at 65 nanometers with just 0.065 microns, 0.028 microns and so on. And probably what we'll study, so this typically refers to your minimum length of the MOSFET. Okay. But that doesn't mean you can't get longer transistors. You're perfectly welcome to use longer transistors. Okay, this is the minimum you can get. And similarly, there will be for each process, let me call this, that this distance is also, there will be a minimum for this distance. Right? Because you just can't, take it close to, such that they're touching or just away. There will be a certain resolution for your, for the distance. That will also change because now what happens is the closer you take it, the more capacitance you get, right? So that will also change for each one of these processes. Okay. So what we'll do is next class we'll stop here today. Next class we'll quickly go through what happens to different parameters of the MOSFET when you actually change, from let's say 0.25 to 0.18 to 0.13 and so on. So that's called scaling. It's called process scaling. Okay. So next class we'll understand what happens when you scale what happens, for example, the width of the GM of the transistor, the different voltages in the circuit, right? We'll understand, what happens to the power dissipation. Okay, what happens to have everybody done, like, let's say a digital ICs course, right? There is each inverter, all these gates have delays, right? So we'll look at what happens to the delay of an inverter, for example. Okay, things like that. We'll study that next class. Okay, see you guys tomorrow from 10 to 10:50, right, in this class.